Okay, so let's continue. So far we have defined a state value function, right? Which is this, and also an action value function. Now we're going to take these value functions, okay, and construct, like, so what is known as the Bellman equation for value. Okay. So probably first I will derive the Bellman equation, and then like I will explain you the significance of this equation. So it's one of the most central equations in reinforcement learning, and almost a lot of like reinforcement learning algorithms can be seen as in some ways approximately solving this equation. Okay, so now let's first do this for value functions, like state value functions. Okay, so v pi of s is given by, as we know, the expected value of gt given st is equal to s, right? Now I can write this as expected value of rt plus 1 plus gamma times gt plus 1 given st is equal to s, right? So we have seen this step already. Now let us expand this and see what happens. Okay, so now this expectation is over the possible probability of taking an action, right? Like the policy. So summation over all possible actions. I'm expanding the expectation here. So what is the probability of taking this action? Okay. Then we sum over all possible s dash and r. Okay, so summation over s dash, summation over r. Okay, the probability of s dash comma r given s comma a, and the inner term is basically r plus gamma times the expected value of gt plus 1 given st plus 1 is equal to s dash, right? So what I have done here is just expanding the expectation. Okay, I'm expanding the expectation with respect to the policy and also the next states and rewards. Like so, summation over a, probability of a given us. This is expectation with respect to phi. So then, for all possible values of, like we are looking for expected return, right? So for all possible values of next state and reward, okay, like what would be the return? So the return is given by reward plus gamma times return from the next state, expected return from the next state, right? So now I can actually, so now can someone tell me what is this particular term here? So expected value of gt plus 1. So it's the state value function for st plus 1, right? So I can just rewrite this as v pi of s is equal to summation over a, pi of a given s, summation over s dash and r, probability of s dash r given sa, okay, r plus gamma times v pi of s dash. Okay, now this equation, okay, so this holds for all states. For every state, its value is defined using expectation over the values of the next state s dash. Okay, now this equation is known as the Bellman equation. So named after Bellman, who did a lot of foundational work on Markov decision processes and dynamic programming approaches that we are going to see in today's lecture. Okay, yeah?
Yeah, I just want to be sure, right next to the bracket, it's R.
Okay, so yeah, so that's what I'm telling from the beginning. So my R's and gammas are confusing. So how do I fix it? So I try to do this for gamma, okay? And if I don't do that, it's R.
Okay.
Okay. It's too bad that they chose to use gamma for discount. Like they could have just used beta for discount.
Also, I complete the circle.
Sorry?
When you go like above for gamma, just complete the circle.
Ah,
Make it even more clear.
okay, like this.
Yeah.
Okay, yeah, I can do that. Okay, so now this Bellman equation is defining the current, like value of the current state based on some expectation over the values of the future states, right? Like so now when you have, let's say, k states, then these are basically k equations with k unknowns, right? Like which are basically the values of these states, right? So now this system of equation has a unique solution, okay? So the unique solution to Bellman equation is basically the value function. Okay, you'll get exact equivalence when you have achieved the value function for the given policy. Okay, now we can also visualize this equation in terms of like what the book describes as is a backup diagram for VPy. Okay, so the backup diagram, like which we are going to use for different algorithms that we are going to see in the future, like will tell you how we construct the equation. Okay, so in the case of this Bellman equation, like you started with a state, okay, and you consider a policy which takes different actions. Okay, the actions are going to be represented with small dots. These are actions. Okay, now for each action, it leads you to a bunch of possible states, right? Like, so maybe this action leads you to two other states. This action leads you to two other states. This action leads you to two other states. Okay, these are like S dash. Okay, now one way to look at how Bellman equation is constructed is by looking at this diagram. Like you first compute or like find the values of these states, like S dash, then you back up these values to the value of state S. And the backup is based on this equation. Is that clear? And in Bellman equation, we are really averaging over all these value functions. Like you have like a bunch of possible next states, and you average over all the paths that leads to the next stage, and that is your expected return from the current state. Is that clear? Okay, so now let us see some example. Now, I think the second part of your first assignment will force you to implement these things by yourself, like, but we are going to see some examples in the class. I don't know if I have it. Okay, I have it here. Okay, so now in this case, I have a simple grid world. Okay, so we are going to see several such grid worlds in the course. Okay, so these are nice because like they are simple and like easy to run experiments with when compared to like really complex settings like playing chess or Go or Atari, right? Like so in this case, it is like a 5x5 grid world where the agent moves in the grid. Okay, now the agent can take 4 actions. It can go up, come down, or take left or take right. Okay, so there are 4 possible actions. Now, for this specific grid, the agent is going to get a 0 reward for every transition. Like for example, if it moves from here to here, it gets a 0 reward. Okay. However, if it tries to move outside the grid, let's say it tries to move like this, it cannot move. It's going to stay there, but it gets a reward of -1. So it is penalized every time it tries to come out of the grid. Otherwise, it's just a 0 reward. But there are these 2 like good states, like A and B. Whenever you go to A, you take any of the 4 actions. It takes you to state A dash, and also gives you a reward of +10. Okay. Similarly, whenever you reach B, you take any action you want, it will take you to B dash and gives you a reward of +5. Okay. Now, let's forget about the right-hand side. If I put you in this grid world randomly, okay, so here, what would your behavior would be? Okay, we'll move to the right. Maybe tell me the high-level strategy. So it's going to be a long game if we say step by step. So what would be your high-level strategy here? Reach A, right? So you start here, you would try to reach A because it's going to put you here and you get plus 10. Okay, once you come to A dash, what would you do? Again go to A. Now this is your policy, right? Like you will keep getting plus 10, plus 10, plus 10, right? So now the goal is to design an agent which will automatically figure out this policy, okay? Now, before we do that, so let's say I have an agent which has equal probability for taking any action. Okay, so we're going to consider equiprobable random policy. Okay, now for that policy, where like the probability is equal, like the probability of from here, if I take action left, then the probability of going here is 1. Okay, so and from every place you have equal probability for taking all the 4 actions, 1 by 4, 1 by 4, 1 by 4, 1 by 4. Okay, so now you know the probability functions, like you know the policy probabilities. You also know the world very well, like you know the dynamics, right? So now you can actually implement the Bellman equations and solve the Bellman equation. Okay, so we are going to see how to solve the Bellman equation very soon. But for now, let us say that you have the system of equations, you solve it, and you get the values, right? Now this is how that value is going to look like. Okay, so now let's try to understand how this value is looking like, right? So it already tells us a lot of interesting things about Bellman equation. Okay, so you can see that in the corner, it also tells us like what is the intuition for like what is a value function. Okay, so you can see that in the corners you have negative value, which means it is not a good idea to go to the corner, and it is even more negative in the 4 corners because well, not the 4 corners. In the top you have A and B. This corner is like more negative than the edges because you have one like 1 by 2 probability of going outside, right? So which means like you are going to get more negative rewards. So in some sense, these values tell us like what to do roughly in these states. And another interesting thing that you can see here is because we have this equiprobable policy, right? So state B, which has actual return of 5, is estimated higher than 5. On the other hand, state A, which has a return of 10, is estimated lesser than 10. So can someone tell me why? Yeah? No, why? Why is the question? Yeah?
I think the next step of A and B, the A is further than B. So if we are going to receive a lower reward, and the actual state value is going to be less than.
Okay, is it just that? So for people in the chat, like in the Zoom, I think the answer was like it takes a little bit more time to reach A again from A dash, right? Like roughly. Okay, any other answer? Yeah.
I think when you go from A to A prime is next to plus minus prime river.
Yes, that is another reason, right? Like so, both are valid reasons. Like the second reason is A dash is more close to the negative rewards than B. The probability of bumping into negative rewards is more in A dash. So in some sense, it's safe. So given the fact that you don't have control over the policy here, like in this case, it's a random policy. If you have control over the policy, then these value functions are going to be different, completely different. Okay, so that is why it is important that you define value functions with respect to policy. So in this case, the policy is random policy. You don't have control over the policy. Then if you want to be safe, it is safe for you to go to B than A. Okay, because if you go to A, there is more chance of getting into negative rewards than B. Is that clear? Okay, so now similarly, I can also write the Bellman equation for Q pi of S comma A. Okay, yeah, question?
So we start off with the policy where we have equal probability for all the actions. But once we update the grid which we have, when the policy change, now that we know.
Okay, so we haven't come to that part yet. So far, like we just described how to evaluate a policy and construct the value function. Okay, so I'll come to that question probably in like 5-10 minutes. Okay, so now let's construct the Bellman equation for Q functions. Okay, so Q pi of S comma A. I'm going to directly write it. Okay, you can derive it as an exercise. Is basically summation over S dash R, probability of S dash R given S comma A. Okay, R plus gamma times summation over A dash pi of A dash given S, Q pi of S dash A dash. Okay. Now, our goal is to have the expected return, right? Like in this case, I don't have access to state functions. Like I only have access to Q functions. Now, you can see that this particular part, right, which considers all possible next actions and their Q values from state S dash, right? So that is actually the state value function. So since we don't have access to state value function, we are using the Q functions to construct it. Okay, so this is this clear? So now let's look at the backup diagram. 1 second. So now let's look at the backup diagram on how this works. Like so in this case, you have we have a state action pair. So from the state action pair, like with some probability, like you reach future states. Okay, now you also receive some reward. Now we don't have the values of these states to back up. Okay, so we are going to construct or compute the values of these states by considering the Q values from based on pi. Okay, so you consider the Q values of all the actions from the next states. Okay, and then you do the backup. Okay, so you back all the way up to the Q of S comma A. Question?
Yeah, so it's a question about, I guess, this in the value function. You said like the only solution to these equations is like the Q value function or the value function. So here, like there's is the policy dependent on gamma? Because if it isn't, like if you vary gamma, just like that's essentially the question. Like, is the policy dependent on gamma to make the equations work?
Well, when you are estimating the values, right? Like so, why would the policy be dependent on? Okay, I think the confusion is because we are trying to like think about both simultaneously, but we haven't reached that state yet. Like so, for now, policy is given. Okay, now you can pick whatever gamma you want and construct the value function. For any gamma that you are picking, there is a unique value function. Okay. Yep.
When we have the state and the action, why it makes the step we have two other states. When we know the action, we should have one other state in the backup diagram.
Sorry, can you repeat?
Yes. Let's say we have a state S1 and we take the action A1. So we are going to another state.
Yes.
It's a unique state, but in the backup diagram you have two other states.
Oh. No, when you take an action, you don't. No, it's a probabilistic. It's a distribution over next states, right? Like so, you can have many possible next states.
Based on one action?
Yes. That is what probability of S dash given S comma A is, right?
But when you, for example, when you need to read, you just choose left, right.
This is a very deterministic grid, right? Like, but I can actually construct a stochastic grid where there is wind playing some role, and every time you try to move right, with probability 0.8 you move right, but with probability 0.2 you move left, right? Like so. So the world is not deterministic. So you take the action again and again, maybe you will see different reactions. Like so the world is always stochastic most of the time. Yep.
That formula like, of the policy A dash given S, and the process like A dash given S dash. So like, which is the correct one?
Okay, it's S dash. Yeah. Okay, so I think we have so far we have talked about value functions and also Bellman equations for these value functions, right? So now, as several questions pointed towards, like, so what is our goal for doing all these things? Our goal for doing all these things is to find the optimal policy, right? Like, so now let's talk about optimal policies, okay? And when you have an optimal policy, that policy will have some value function, right? And we're going to call those value functions as optimal value functions. Okay, now, to say this is an optimal policy, we need a way to compare policies, right? Like, let's say I give you two policies, pi and pi dash. Okay, can someone tell me when is pi greater than or equal to pi dash? When can you say that policy pi is better than some other policy pi dash? Sorry? Okay, so when you get high reward by using a policy, is there any other way to define it? Yep.
When you get a better expected.
When you get better expected return, and how would you estimate that? Yep. Okay, so by comparing the value functions, right? Like so I'm going to define pi to be greater than or equal to pi dash if and only if v pi of s is greater than or equal to v pi dash of s for all s. Okay, now this is important. Like so, I can have two policies, and let's say there are 10 states. I'm going to compare the value of these states when using both the policies. If it so happens that one policy has strictly better value function than another, like at least greater than or equal to, like so then like if it has equal value, well, we'll talk about what if pi and pi dash has really equal value functions. It's a very special case. But for example, let's say out of 10 states, in 9 states, they have same value, but there is a 10th state where they have one policy has different value. Then it just means that this policy has found something better than the other policy. So it should be better than the previous policy, okay? Now, the moment we start ordering policies like this, right? Like, so one is better than another, and another one is better than another, and so on. Now, there should be this one policy which is better than everyone else, right? So there always exists at least one policy, okay? So that is better than or equal to all the other policies. We're going to call that as the optimal policy. Okay, so the optimal policy is represented as pi star. Okay, pi star means that is the most optimal behavior or policy that one could have in this particular environment. Yes, question?
I'm not clear, like, why do you know that optimal policy exists? Like, why do you know that there is one policy which is better than every other policy on all other states? Not the single state.
Okay, so we will not get into the theoretical arguments, at least for this year's course, okay? So, but I can give you some intuitions, okay? So the fact that we can actually order policies, and the fact that like there exists like some ordering, right? Like so, like given any two policies, I can always compare and say which one is better. And okay, I'll come to that, right? And the fact that we are in a finite MDP setting, like which means, let's say you have k, let's say you have n states, okay, and you have k actions possible. Can someone tell me how many possible policies are there? So I have n states and k actions possible. So how many possible policies exist? Simple n power k, right? Like, so there are finitely many policies. Okay. There's also another catch. We are looking at deterministic policies here. Like, we are not talking about stochastic policies. But most of the theory holds in stochastic setting, but we will not discuss in detail in this class, okay? For the moment, consider deterministic policies. There are n power k deterministic policies possible, and we have an ordering over all of them. So I'm going to define what is an optimal policy. It is basically max pi over all these policies, yeah?
Does the definition only hold for deterministic policies?
Sorry?
Does this definition of like greater than only hold for deterministic policies?
No, it also holds for stochastic policies, but the convincing argument for him is going to be a bit more complicated, so I'm not going to do that.
I mean, like, sometimes, like, some policies are not even comparable, right? So, like, this policy is better than the other policy on some states, but not on other states. Like, you can't really decide between, like, it's not a complete ordering, right? It's partial ordering.
Yes, that's a good point. Okay. Yeah, that is a good point. You might have some issues with that in stochastic settings, but definitely not in deterministic settings. But probably I will think a bit more about it and give you better arguments later. Okay. Okay, but in deterministic setting, the things are simple. Okay, so like we have a unique policy. Like, so in fact, we can prove that there exists an optimal policy, but we are not going to do that proof here. So pi star is the optimal policy. Now, when you have an optimal policy, you should also have the corresponding state value function, right? Like, so let's just call that as V star. So V star is the optimal state value function. Okay. Now V star of S is defined as max over pi V pi of S for all S belonging to S. Okay. Now it's basically the maximum possible value that you can get when you search over all the policies. Okay. Now similarly, we can also construct Q star of S comma A, which is optimal Q functions for optimal policy, right? Like, which is max over pi Q pi of S comma A for all S belonging to S and A belonging to capital A. Okay. Okay. Now we can relate Q star and V star. Okay. So Q star of S comma A is equal to expected value of RT plus 1 plus gamma times B star of ST plus 1. Given ST is equal to S, AT is equal to A. Okay, yeah.
Does policy only give us what to do in a state, or does it also give some kind of an ordering which have to follow to?
No, pi is just you're talking about pi, right?
Yeah, right.
So pi is just a mapping from state to action. It gives you a probability distribution over the actions. Okay, now we have, okay, so we have defined what is an optimal policy, and we have also defined the value functions of optimal policy, right? So now this V star, right? Let's talk about V star first and then about Q star. So this V star is a value function for some policy, right? Like in this case, it happens to be optimal policy, right? It means V star should also obey Bellman equations, right? Now, when we write the Bellman equation for V star, like what is interesting about V star when compared to other V's is it can be written without reference to any specific policy because it talks about the optimal policy, right? So I can just simply write V star of S to be max over all possible actions Q pi star of S comma A. Okay, now this is max over actions expectation with respect to pi star GT given ST is equal to S, AT is equal to A. Now this is max over A expectation with respect to pi star RT plus 1 plus gamma times GT plus 1 given ST is equal to S, AT is equal to A. I'm really redoing the Bellman equation here, okay? So we are going to get the Bellman equation. So this is equivalent to max over A, expected value of, okay? You can see that I dropped pi star here. So RT plus 1 plus gamma times V star of ST plus 1. Okay, this is V star of S. Given ST is equal to S, AT is equal to A. Okay, now I can also expand the expectation. So V star of S is equal to max over A, summation over S dash R, probability of S dash R given SA, R plus gamma times V star of S dash. Okay, now this Bellman equation for optimal value function, right? Like, so this is Bellman optimality equation for V star. Okay, so now let us try to draw the backup diagram and see how this is going to look like, right? Like, so now in this case, you start with S, okay, and you have many possible actions, right? Now, if you remember the initial Bellman equation, like it was summing over all possible actions, right? But the optimality equation would take a maximum over these actions, okay? And for each of these action, you get the next states, and here you have to do the summation, okay? Now, the only difference between this backup diagram and the usual Bellman equation backup diagram is that we have this max here, and you don't have that max in the other one. Is that clear? Any questions? Okay, so let us also write similar let's write similar equations for Q star. Q star of S comma A, again I'm going to write it directly, you can derive it if you want, is expected value of RT plus 1 plus gamma times max over A dash Q star of ST plus 1 comma A dash given ST is equal to S, AT is equal to A. Okay, so now again, if you want to compare this with the Bellman equation for Q, right? So you don't have the max here. Instead of the max, you're going to have summation over all possible actions, if you remember. So this is simply summation over S dash R, probability of S dash R given S comma A, R plus gamma times max A dash Q star of S dash comma A dash. Is that clear? So we can also draw a corresponding backup diagram, which is going to look very similar to the Bellman equation backup for Q, but you have a max here. So you start with S comma A. With some reward, you go to new states, right? For each of these new states, in the past, we were summing over all possible actions. Now, instead of summing, sorry, we are going to max. Okay. Okay. So now, for finite MDPs, okay, as I mentioned before, for the Bellman equation, the same thing holds for Bellman optimality equation. Okay, so the Bellman optimality equation for V has a unique solution independent of the policy. Okay, so if there are n equations with n states and n unknowns, right? Like so, if you know the dynamics, you can solve this system of nonlinear equations, and you are going to find the optimal policy. And once you have the optimal, so you're going to find the optimal value function. And once you have the optimal value function, then it is easy to construct the optimal policy, right? So now let's actually go back to our grid world example. Okay, in this case, this is the solution for Bellman optimality equation. Okay, which means this is the most optimal value function for this particular task. Okay, and how to construct policies from value functions, right? Like, so now this is where, so far we were assuming given a policy we construct a value function. Okay, so now we are going to see the other way around and see how these things interact. So given this value function, how to construct the policy? Okay, let me tell you let's take an example state. Let's say I am in this particular state. Okay, now can you tell me what is the optimal action to take in this state?
Top and left.
Top and left, right? Like they're both 17.8. So you can see that the optimal policy is top and left. Let's take one more example, right? Like, so let's take this set. So you can see that 17.8 is the highest. So the policy is here. So as you can see, once you have the value function, it is very easy to construct the optimal policy. And you can convince yourself that this optimal policy is indeed the best behavior possible in this grid world. Okay. Now, this means we have solved the MDP problem, right? Like, so do we need, like, well, which means if you construct your reinforcement learning problem as an MDP, you have a solution here. So is that end of the world? Like, so is there any issues with this solution? Yeah.
Let's say we are in the E, and the answer says that the optimal solution is going left, right, down, and top.
Oh yeah, because it's because of the construction of the world. So if you remember, when you are in A and B, you can take any action you want. It always takes you to B dash and A dash.
Oh.
Okay. Now, as we have seen today, like explicitly solving this Bellman equation is giving me the optimal behavior for any environment, right? Like, so now, are there any problems with this? Like, if not, we can just take any problem, reinforcement learning problem, and then I can just find the optimal behavior, right? Like, so what are the issues with the setup that we have discussed so far? Anyone? Yeah?
Solving Bellman equation for large models are difficult.
Solving Bellman equations is very difficult or computationally intensive when you have millions of states. Okay, any other issues? Yep.
We often don't know how the environment.
Yes, that's a very good point. We often don't know how the world works. We don't have access to the dynamics function, P. That's a very strong assumption, right? Like, so maybe I'll write them down. Like, so there are some strong assumptions made by this explicitly solving Bellman optimality equations. So like the first one is we accurately know the dynamics of the world, which is often not true. And the second issue, Mazia pointed out, is we have enough compute to complete the solution. Okay, that's a very strong assumption. Like I can give you, I think I already gave you the backgammon example, right? Like, so in backgammon you have 10 power 20 states. So solving Bellman optimality equation for backgammon is just infeasible. Yeah.
I have a question actually. So when you have an RL problem like this, do you solve the Bellman optimality equations or do you solve the other equations? Bellman regular equations.
Well, you care about optimal policy, right? So
no, I mean the issue is that it's about again the computation, right? So the optimality equations were non-linear because of that max, and the other ones were probably linear. But you can probably like do more of.
That's a very good point. So in practice, we will solve the other Bellman equation. We are going to see that very soon. Yeah. So as okay. So what's your name?
Kunal.
Krunal. Okay, so as Krunal rightly pointed out, this is a system of non-linear equations, right? Like, so on the other hand, the other equations was much simpler. It's a system of linear equations, and there are efficient linear programming solutions available to solve that. But the problem with solving the I think we are jumping too much into the next part of the lecture. But the problem with solving just the Bellman equations instead of optimality equations is Bellman equations are defined for one policy, right? So then there is a question like, so what is this policy? Like, and how do I use this solution to come up with the optimal policy and so on? So that is exactly the topics that we are going to cover very soon in few minutes, okay? But for now, let's talk about the Bellman optimality equation. So there are few strong assumptions here. One is, you know, the dynamics, which is not true always. Second, you have compute to solve the problem, which is also not possible always. And the third important problem, like assumption, which we make, probably which we will not relax for most of the course, but we will relax towards the end of the course, is the Markov property. Okay. So real world is not Markovian. It's not at all, not even close to Markovian. Okay, so the real world is highly non-Markovian. Like, there is always uncertainties and like partial observabilities in the world, which makes it sometimes impossible to construct a state. Okay, so then what do we do in such situations, right? Like, so this Bellman optimality equation doesn't talk about that at all. Okay, so but we are going to talk about that in the future. Okay, but as I mentioned before, like, all of reinforcement learning is about how to solve this Bellman optimality equation efficiently and also without access, mostly without access to the real dynamics function. Okay, so it's a very challenging problem. Okay, so we're going to see at least 3 types of solutions like in the next few lectures. Okay, so let's start with the first setup, like first type of solution, which is the idea of dynamic programming. But just to make it easy for having complete videos in YouTube, so we are going to, well, let's just stop here. So we are finishing a topic. So instead of taking break up to 11:30, we're going to take break from 11:15 to 11:25. So we're going to have a slightly longer third part. So we will continue at 11:25.